Welcome to the Deep Dive, where we unpack a stack of information and get straight to the core of what you need to know. Today, we're taking a really fascinating journey, diving right into the heart of the devices many of us, well, can't live without, Android. Our listener for this deep dive is super curious about what makes these mobile applications tick. They've shared a rich set of sources with us, including some excellent lecture notes on mobile application development. So if you've ever wondered how the apps on your phone really come to life, how they interact, or maybe even why they have those quirky dessert names, you're absolutely in for a treat.
Yeah, what's fascinating here is that we'll be breaking down Android from its foundational operating system all the way up to the UI elements you tap and swipe every single day. Our mission today is really to distill the essential concepts and maybe some surprising facts that make Android such a powerful and, let's face it, undeniably popular platform. Okay, let's unpack this.
So let's maybe kick things off with the big picture. Most of us think of Android as the mobile operating system, right? But from what we've seen in our sources, it's really blossomed into something much broader, hasn't it?
Oh, absolutely. Android, developed by Google, it's built on a modified Linux kernel and other open source software that makes it incredibly flexible. While its primary home is, yeah, touchscreen, mobile devices, smartphones, tablets, its reach has expanded, like dramatically.
Yeah.
Google has crafted specialized interfaces for Android TV, Android Auto, Wear OS for watches. We're even seeing variants pop up in game consoles, digital cameras, even some PCs. Kind of begs the question, how did it get so dominant in so many different areas?
It certainly did. And from our sources, it seems a couple of key ingredients for its runaway success were its open source nature, meaning anyone can customize the platform and just the sheer abundance of low-cost apps available.
Indeed. And this open source thing, it really ties into a fun tradition the Open Handset Alliance, the OA, maintains. They're the group responsible for Android's ongoing development, right?
Mm-hmm.
And they decided early on to name each major Android version release after a dessert. We're talking Cupcake, that was 1.5, Donut 1.6, Eclair,
Oh, yeah.
Froyo, Gingerbread.
I remember those.
Yeah. While the very first versions, 1.0 and 1.1, didn't get these sweet monikers, the tradition really took off. Honeycomb, ice cream sandwich, jelly bean, Kit Kat, lollipop, marshmallow. It just kept going alphabetically. It's a kind of a playful nod to the constant evolution, and once a version is out, boom, its source code is released too.
That's such a sweet detail,
Yeah.
literally. Speaking of Jelly Bean, Android 4.1, that SDK, released back in July 2012, introduced some really significant features. Beyond just adding new functions, was there like a bigger strategic aim with that particular update?
That's a great question because, yeah, this release was a major turning point, not just, an incremental update. Take Project Butter, for example. That wasn't just about technical speed. It was a fundamental shift towards prioritizing perceived performance. Fluidity. They actually boosted CPU performance on touch events and started predicting your finger movement, all to make the UI feel incredibly fast and responsive.
Oh.
This focus on smooth interaction became like a cornerstone of Android's user experience strategy. It directly impacted how it could compete, making the device feel, well, truly premium.
So it wasn't just about raw speed numbers, but making the whole experience feel more intuitive, more natural for the user. What else stood out from Jelly Bean that improved, daily use?
Precisely. It also brought faster speech recognition that, and this was huge, didn't require an internet connection.
Oh, wow.
Massive leap for usability on the go. The notification system got a major overhaul too. You could see richer displays with pictures, lists, even action buttons right there in the notification.
Hand.
Yeah. We also saw support for new languages like Arabic and Hindi, and a significantly improved predictive keyboard. And on the accessibility front, Jelly Bean added an auto-arranging home screen for icons and widgets, which was nice, plus a gesture mode combined with voice output for visually impaired users. Even the camera app got better with a new review mode.
And for security and seamless communication, what did Jelly Bean bring to the table?
Well, it really pushed the envelope for device communication using near-field communication, NFC, and also Bluetooth Simple Secure Pairing. Made connecting things easier. We also saw an improved Google Voice search, sort of like Apple's Siri, becoming more robust. And for security, Face Unlock got an optional blink confirmation.
Oh, yeah, I remember that.
Yeah, a clever way to make sure it wasn't just a photo unlocking your device.
And for information on the go, Google Now was a pretty big deal, wasn't it?
Google Now was, yeah, a game changer. It was designed to give you just the right information at just the right time.
Mm-hmm.
It used these context-aware cards. So imagine seeing nearby restaurants as you walk by, or train schedules when you're near a station, all without you explicitly searching.
Kind of predictive.
Exactly. Google Play widgets also gave quick access to media, even suggested new purchases. Google search got faster, more accessible from the lock screen, and importantly for developers, anti-piracy features were added. They encrypted applications with device-specific keys, making unauthorized copying much harder. It was really about making the whole ecosystem robust for both users and creators.
That's a fantastic overview of how Android evolved, especially with Jelly Bean. But all this functionality, it has to be organized somehow, right? How does Android actually structure itself internally to handle everything from like low-level hardware stuff up to the apps we use? Our sources talk about a software stack.
Yeah, think of Android like a layered cake. That's a good analogy. A stack of software components. Each layer rests on the one below, and it's all built on top of a modified Linux kernel. This architecture is roughly divided into 5 crucial sections, 5 layers, each one essential for the whole system to function.
Okay, that layered cake analogy helps to visualize it. So what's at the very bottom, the foundational layer of this cake?
At the root, forming the base, is the Linux kernel. This isn't just any Linux kernel. It's a version modified specifically for mobile constraints. It's responsible for all the core system services, device drivers, power management, memory management, handling processes, security.
The real guts.
Exactly. It handles all the low-level interactions with the hardware. It's the foundation everything else relies on.
And what's the next layer up, building on that kernel foundation?
Next up are the native libraries. These act as critical middleware. These aren't just generic libraries. They're high-performance engines powering key functions. You've got WebKit in there. That's the web browser engine. So Android has browsing built right in. Then there's lib, a standard C library, Squite for robust local data storage. Tons of apps use that. Plus, libraries for audio, video, sophisticated graphics like OpenGL for 3D, SGL for 2D rendering, making sure visuals are smooth. And the FreeType library handles fonts. These native components are why Android can do so much, from browsing to gaming.
So the actual applications, the apps we download, they aren't running directly on the Linux kernel then. That seems like quite a leap.
Right, and here's where the clever design really comes in. Applications run on the Android runtime layer. This layer contains core libraries and something called the Dalvik Virtual Machine, or DVM. Now, the DVM is specifically optimized for mobile devices. It's kind of like a Java Virtual Machine, a JVM, but engineered to use less memory and offer faster performance. It smartly leverages Linux's core features, like memory management and threading. And here's the genius part. Each Android app runs in its own isolated process, with its own instance of the DVM.
Okay.
This provides stability and security. If one app crashes, it usually doesn't take down the whole system.
Fascinating. And above that runtime, where developers actually, interact more directly.
That would be the application framework. Think of this layer as Android's massive toolkit for developers. It provides all the high-level services needed to build apps, exposed through Android APIs, application programming interfaces. This includes things called managers for handling activities, packages, windows, content providers for structured data sharing between apps, and view managers for building the UI elements, the buttons, text fields, lists.
So it's the bridge.
Exactly. It's the bridge, allowing developers to access underlying system capabilities without needing to mess with the kernel or native libraries directly.
And then finally, at the very top of this whole stack, where the magic happens for us, the users.
That's the applications layer. This is where all the apps you use every day live. Your home screen, contacts app, settings, games, browsers, everything. Any application you write, whether it's a simple calculator or a complex social network, sits at this very top layer. And it relies seamlessly on the framework, the runtime, and the libraries below it, all ultimately powered by that foundational Linux kernel. It's the entire user experience, delivered through this carefully constructed hierarchy.
That tiered structure, yeah, that makes so much sense now. So for anyone listening who's maybe now inspired to build their own Android app, getting the right tools is definitely the first hurdle. Our sources detail the process for installing Android Studio and the SDK. What's the absolute first thing someone needs to do?
Right. The absolute first step is setting up your development environment, your IDE. For Android, that's primarily Android Studio. Before that, though, you need the Java Development Kit, the JDK. Version 8 or higher, installed on your system, Windows, Mac, Linux, whatever. Then you install Android Studio itself, following the steps for your platform. But crucially, after installing Studio, you need to use its built-in Android SDK Manager. This manager lets you download essential packages, the FDK tools, platform versions for specific Android releases you want to target, various support libraries. It's like gathering all the specific ingredients you need before you start baking your app cake.
So the SDK Manager sounds like this central hub, keeping track of all the different pieces you might need.
It absolutely is. It ensures you have everything required to develop for different Android versions, different device types. Once you have that installed, a core part of testing, especially without needing a huge pile of physical devices, is setting up an Android virtual device, an AVD.
An AVD, what exactly is that? Is it literally like having a phone running on your computer screen?
Pretty much, yeah. An AVD is essentially an emulator configuration.
Mhm.
It represents a specific Android device because there are so many Android devices out there, right?
Yeah.
Different screen sizes, hardware, Android versions.
Right, fragmentation.
Exactly. AVDs let you test your app's compatibility across this vast landscape without buying 100 phones. You can define parameters like the Android version, its API level, the size of a virtual SD card, even the screen dimensions or the skin of the virtual device to mimic a specific model.
So it's like having a virtual lab, full of different phones and tablets, all customizable to test your app in various scenarios. That's actually really clever.
It is. The emulator provides most hardware and software features of a real device. Obviously, you can't make actual phone calls on it.
Right.
But you can simulate navigation, control keys, interact with network services, audio, video. You can even simulate incoming SMS messages or fake phone calls for debugging purposes. It's incredibly powerful for getting most of your testing done efficiently.
But there must be some limitations, right? They can't be a perfect substitute for the real deal.
You're right, they're not perfect. While super useful, emulators can't fully replicate actual device limitations, like specific CPU bottlenecks or real-world memory constraints. They simulate features like GPS and sensors, but they don't fully support peripherals like cameras or USB Bluetooth connections in the same way a physical device would.
Okay.
So, for that crucial final stage of testing, making sure it really works well in the real world, a physical device is still incredibly important.
Okay, so once you've built an app, tested it on the emulator, maybe fixed some bugs, how do you get it onto a real physical device?
It's fairly straightforward usually. You connect your phone or tablet to your computer via a USB cable. Then you need to make sure your debugging configurations are set up correctly in Android Studio. And crucially, you have to enable USB debugging on the device itself. It's usually buried in the settings somewhere.
The hidden option.
Exactly. For Android 4.2 and newer, there's that little Easter egg. You have to go into settings, find the build number, and tap it 7 times.
7.
Yep, that unlocks a hidden developer options menu, and that's where USB debugging lives. Once that's enabled, Android Studio makes deploying your app directly to the connected device pretty easy.
Okay, we've covered the OS, the tools. Now let's zoom right in on the actual applications themselves. What are the core components that make an Android app function? It sounds like there are some key foundational elements every developer really needs to grasp.
Absolutely. Our sources pinpoint 4 fundamental building blocks. Think of these as the core concepts every Android developer lives and breathes. They are activities, services, intents, and broadcast receivers, and content providers, and all the crucial information about these components, how many there are, what they do, what permissions they need. It's all meticulously defined in one central file, the Android manifest.xml. Think of like your app's passport and instruction manual for the operating system. The system reads this before running any of your code.
Okay, the Android manifest. Got it. So let's start with the first one. Activities. What role do they play in what we actually see and interact with?
Activities are essentially the visual presentation layer. They represent a single screen with the user interface. A good analogy is a single web page in a website. Most apps, of course, have multiple activities. Your login screen might be one activity. The main application dashboard could be another. Maybe a settings page is a third activity. And there's usually one designated as the main activity that's the primary entry point when you launch the app.
And how do these different activities interact within an app? You said they're like single screens, so they seem quite independent.
They are pretty independent, yeah.
Yeah.
But they're cleverly managed by the Android system using something called a backstack. When a new activity starts, the previous one isn't destroyed, it's just pushed onto the stack and paused.
Okay.
Then when you press the back button on your phone, the current activity is popped off the stack and destroyed, and the previous one is brought back to the front and resumed.
Ah, like a stack of plates.
Yeah, exactly like stack of plates.
Activities also have a very defined life cycle, with important callback methods the system calls at different stages. Things like onCreate when it's first initialized,
Yeah.
onResume when it becomes visible and interactive, onPause when it loses focus, and onDestroy when it's finally terminated. Understanding this life cycle is absolutely crucial for writing stable, well-behaved apps.
What about services then? Our sources called them invisible workers, which is a really evocative description.
It really is a great analogy. Services run quietly in the background without any user interface. They're designed for performing long-running operations or handling tasks, even when the user isn't actively looking at your application.
Yeah.
A music player continuing to play your playlist while you're browsing the web or checking email, that's a perfect example of a service in action.
Right.
Services can be basically started, meaning they run indefinitely to complete a specific task, then they stop themselves, or they can be bound. A bound service allows other components, maybe an activity, to connect to it and interact, almost like a client-server relationship, for inter-process communication. They're the backbone for any continuous, non-UI related work.
Okay, and intents and broadcast receivers, these sound like they're all about communication within the system.
You've hit it exactly. Intents are essentially messages passed between components. They're the fundamental mechanism for communication in Android. You use an intent to start an activity, or to trigger a service, or even to broadcast a message system-wide. For example, an intent might be sent by your app to tell the system, I want to open the web browser to this specific URL, or I want to share this photo using whatever app the user chooses.
Ah, so they trigger actions.
Precisely. And broadcast receivers simply listen for and respond to these broadcast messages. These messages might come from other applications, or they might come from the Android system itself, like an app reacting when the device finishes booting up, or when the battery is low, or when a text message arrives. Receivers can be normal, meaning they run asynchronously and there's no defined order in which multiple receivers get the message. Or they can be ordered, which means they run synchronously, delivered one by one in a specific sequence, and one receiver can even modify the message before passing it on or stop it entirely.
And lastly, the fourth building block, content providers. What's their main job?
Content providers are crucial for managing and persisting application data. Often they interact with underlying SQL databases like SQL. But their most powerful feature and their primary design goal is the responsibility for sharing data beyond the boundaries of your own application. So one app, like your Contacts app, can expose its data through a content provider. Then, other authorized apps can query that provider to access the contact list in a controlled, standardized, and secure way. It's the standard method for inter-app data sharing on Android, making the ecosystem feel more integrated.
That's incredibly important for an ecosystem with millions of apps needing to work together sometimes. So with all these components, activities, services, receivers, providers, how does the Android system actually know about them and know how they're supposed to work together?
That's the critical job of that Android manifest.xml file we mentioned earlier. It's a mandatory XML file always located in the root directory of your app project. And it provides essential information about your app to the Android system before the system even tries to run any of your application's code. This includes your app's unique package name, like com.example.myapp, its version number, a declaration of all its components, every activity, service, receiver, provider. It also lists all the permissions your app requires, like needing access to the internet or the camera or your contacts.
So the user sees those permissions when they install.
Exactly. That comes directly from the manifest. It even defines metadata like the app's icon and the user-facing label or name. It truly is the app's identity card and its instruction manual for the entire Android operating system. It's fundamental.
Okay, so once you have that foundational understanding of the components, the manifest, the next really exciting step is building what the user actually sees and touches, right? The UI. Our sources dive deep into how you actually create those interactive user interfaces.
Exactly. User interfaces, or UIs, in Android are built using a hierarchical structure of objects, specifically view objects and view group objects. The standard and generally the preferred approach is to define the layout of the interface declaratively using XML files. And then you modify and manipulate that interface, respond to interactions programmatically using Java, or more commonly now, Kotlin code. The separation layout in XML, logic in code, makes UI design incredibly flexible and easier to manage.
Can you break down the difference between a view and a view group? It sounds like they work very closely together.
They absolutely do. They're the fundamental building blocks. A view is the basic UI component. Think of it as a single widget on the screen, a button, a text label, an image, an input field. It's responsible for drawing itself in its designated area on the screen and for handling user events directed at it, like clicks or touches. A view group, on the other hand, is typically an invisible container. Its primary job is to organize and arrange other view components, and it can even contain other view groups.
Ah, nested containers.
Exactly. They form this nested view tree structure. This allows you to build complex, sophisticated interfaces from these relatively simple building blocks.
So view groups are like the architectural elements, the scaffolding, that hold and arrange all the individual UI pieces. That makes a lot of sense. And Android provides different kinds of these layouts, different view groups, right?
Precisely. Android gives you a powerful array of layouts, which are all just specialized types of view groups, each designed for organizing child views in a particular way. Probably the simplest and one of the most common is linear layout. It arranges its children sequentially, either one after another horizontally or stacked vertically. You control this with its orientation attribute, and you define the layout width and layout height of its children using values like wrap content, make it just big enough to fit its content, or match parent, make it expand to fill all the space its parent container gives it. Great for simple lists or forms.
Okay.
Then there's relative layout. This one is incredibly powerful, maybe a bit trickier to grasp at first. It positions child elements relative to each other or relative to the parent container itself. So you can say things like, this button should be positioned to the right of that text label, or this image should be aligned to the bottom edge of the parent layout.
That sounds really flexible.
It is. It's fantastic for building responsive designs that adapt beautifully across lots of different screen sizes and orientations. That's crucial in the fragmented Android world. Mastering relative layout really unlocks adaptable UIs. Frame layout is simpler. It's designed primarily to display a single child view. If you add multiple views to it, they stack directly on top of each other, like transparent sheets of paper.
Oh, interesting. What's that useful for?
It's often used for dynamic content switching. Like
Yeah.
maybe you have an image gallery where swiping reveals the next image, effectively hiding the previous one,
Yeah.
or maybe showing loading indicators over content. There's also table layout, which, as the name suggests, arranges children into rows and columns, very much like an HTML table structure. And grid layout, which also uses a grid format, but allows for more precise placement of children at specific row and column coordinates, offering a bit more flexibility than table layout in some cases.
Our sources also mention a layout that's now considered deprecated, absolute layout. What was that and why did it fall out of favor?
Yeah, absolute layout allowed you to specify exact X and Y pixel coordinates for where your controls should be placed on the screen. While it offered, pixel-perfect precision, it's generally avoided and officially deprecated precisely because it's fundamentally incompatible with the huge variety of Android devices.
Different screen sizes.
Exactly. Different screen sizes, different resolutions, different pixel densities. Hard-coding pixel positions almost never works well across all devices. It leads to interfaces that look broken or unusable on screens that aren't the exact size you designed for. It's a good reminder that flexible relative layouts are almost always the better approach for Android.
That makes perfect sense. So once you have these layouts arranging things, what are some of the most common individual UI controls, the views that developers use inside them to let users actually interact?
You'll see these everywhere, every day.
Yeah.
We have the text view, which is simply for displaying read-only text.
Yeah.
And its editable cousin, edit text, which is essential for any kind of user text input. Think login forms, search bars, composing messages.
Right.
Buttons are your standard command elements. You tap them to trigger some action. For selecting options, you have checkboxes. These allow the user to select 0, 1, or multiple options from a set. Think select all the toppings you want on your pizza.
Uh-huh.
And then you have radio buttons. These are typically used together within a radio group. The radio group ensures that only one radio button within that group can be selected at any time. Mutually exclusive choices, like selecting your preferred shipping method, or, as one source mentioned, picking a single WWE superstar from a list.
Okay, so you have these buttons and checkboxes. How do they actually communicate back to the app when a user interacts with them? Like when I tap that submit button, how does the app know what to do next?
That's where event handling comes into play. When you click a button, type into an edit text, or swipe across the screen, that interaction generates an event. The app uses things called listeners, pieces of code, that are essentially registered to listen or wait for specific types of events to occur on specific views.
Waiting for the click.
Exactly. When the event is detected, like that button click, the listener triggers a specific routine or method in your code. Very often for buttons, this is an on-click callback method. Developers can set up these listeners in a few ways, sometimes directly in the XML layout for very simple actions, but more commonly and robustly within the Java or Kotlin code associated with that screen or activity. It's how the app reacts to user input.
And what about those small temporary messages, the ones that often pop up at the bottom of the screen for a second or two, then just fade away? They seem quite common.
Those are toasts, a great name for them. They're designed specifically to display brief, non-intrusive information for a short period. Crucially, they don't block user interaction with the rest of the screen, and they automatically fade out after a set duration, either short or long. They're perfect for quick feedback, like confirming settings saved, or maybe subtly warning you, please enter your username, if you left a field blank in a form. You can control how long they appear, roughly where they appear on the screen, though usually bottom center is default. And you can even create custom-designed toasts if you want something fancier than the default gray box. It's a quick, friendly way to give feedback without interrupting the user's flow.
So a toast to tell you your login was successful? I like that. Simple and effective. Building an app, as you said, isn't just about writing the code. It's also, maybe even more often, about fixing it when things inevitably go wrong. Our sources introduce us to some powerful debugging tools. When an app isn't behaving as expected, where did developers even begin to figure out why?
That's right. Debugging is a huge part of development. One of the first and most fundamental tools a developer reaches for is the Android Debug Bridge, usually just called ADB. It's this incredibly versatile command line tool that lets you communicate directly with either a physical device connected via USB or an emulator running on your computer. ADB is actually a client-server program under the hood. It lets you do things like install apps, uninstall apps, debug them, transfer files back and forth between your computer and the device, and even access a Unix shell directly on the device itself. It's like having a direct command line into your phone's operating system.
Wait, hang on. You can actually access the device's underlying file system and even its databases directly from your computer's command line. That sounds like incredible power for debugging.
Yes, you absolutely can, and it's extremely useful. With ADB, you can use shell commands to navigate through the device's file system. You can go into your app's private data directory, find the database file, usually a SQUAD file, and then use the SQUITE3 command line tool, often included or easily added, to browse the tables and run SQL queries directly on your app's local database. Wow. It's incredibly powerful for understanding exactly what's happening with your data. Is it being saved correctly? Is it corrupted? Is that query returning what you expect? You can see it directly.
Okay, so ADB is powerful for low-level access. But beyond the command line, Android Studio itself must have an integrated graphical debugger, right, for stepping through code.
It does, and it's absolutely indispensable for day-to-day debugging. The Android Studio Debugger is a key feature. It allows you to set breakpoints in your Java or Kotlin code. These are specific lines where you want the program execution to intentionally pause when it reaches that point. When the program pauses at a breakpoint, you can then step through your code line by line using commands like step over, execute the current line and move to the next, or step into, if the current line calls a method, jump into that method's code. While it's paused, you can examine the current values of all your variables in real time. See how they change as you step through. You can trace the entire program's execution flow, follow the logic, and pinpoint exactly where and why a bug is occurring. It's truly like having X-ray vision for your code, helping you diagnose even the most complex issues.
What about those small pop-up windows that sometimes appear? The ones that sort of interrupt you and demand your attention, asking for input or a decision.
Ah, yes, those are dialogues. They're small, non-full-screen windows that typically overlay the current activity, specifically designed to prompt the user for an immediate action or decision. The most common type you'll see is an alert dialog. This can display a title, a message, and up to 3 action buttons typically label something like OK, positive, cancel, negative, and sometimes a third neutral option like remind me later.
Right, confirmation boxes.
Exactly. There are also more specialized dialogues built in, like date picker dialog and time picker dialog. These provide a standard, consistent interface for users to select dates and times, which are obviously very common in apps like calendars, reminders, or booking systems. Dialogues ensure the user focuses on a specific, often critical decision before proceeding.
And what if you want to create a more modular user interface, especially thinking about those different screen sizes, again, like having maybe 2 distinct functional sections side by side on a tablet, but needing them to be separate screens on a smaller phone?
Here's where fragments come in, and they were a really significant addition to Android, a game changer for UI design. Fragments are often described exactly as you said, as pieces of an activity or sometimes sub-activities. Before fragments were introduced, that was back in Android Honeycomb, API level 11, primarily for tablets, initially you could generally only show one activity filling the screen at a time.
Right.
Fragments changed that paradigm. They allow you to divide your UI into multiple, independently managed modules or sections, each with its own layout definition and its own lifecycle events.
So on a larger screen like a tablet, you might indeed have one activity hosting two fragments side by side, maybe a list on the left and details on the right. But on a smaller phone, that same list might be in one activity as a full screen fragment, and tapping an item opens a second activity, which then displays the detail fragment.
Exactly. That's the core idea and the power of fragments. It's a foundational concept for building adaptable, responsive user interfaces that provide an optimal experience across the incredibly diverse range of Android devices, from tiny watches to large-screen TVs now. And importantly, like activities, fragments also have their own life cycles, with callback methods like on Create View, where they create their UI, and on Destroy View, where they clean up resources. These fragment life cycles are closely tied to the life cycle of their host activity. They're a key tool for modern, flexible Android UI development.
Okay, fragments for modularity. And speaking of common UI patterns, what about displaying just scrolling lists of data, or maybe image galleries? What tools does Android provide for those?
Yeah, displaying collections of data is super common. Android offers powerful UI components, or widgets, specifically for this. We have List View for displaying a vertically scrollable list of items, very standard, and Grid View for displaying items in a two-dimensional scrollable grid. Both of these rely heavily on something called an adapter. The adapter acts as a bridge between your data source, maybe an array of strings or a list of custom objects pulled from a database, and how each item is actually displayed visually in a list or grid. It tells the list view how to draw each row.
Okay, the adapter handles the data mapping.
Precisely. For things like image galleries, or maybe onboarding tutorial screens where you swipe horizontally between pages, the View Pager is the standard component. It allows for animated screen slides, flipping through pages of data or views. And finally, the spinner provides a quick, compact way for the user to select one value from a predefined set. It typically looks like a button displaying the current selection, and tapping it reveals a drop-down list of all the options. Very common in forms.
And one last thing. Sometimes if you long press on an item in a list, or maybe on a specific picture, you see a little menu pop up right there, right?
That's a context menu. It's designed to appear specifically on a long click or long press gesture on a particular UI element. It offers actions that are directly relevant or contextual to the specific item you pressed. As a developer, you register a specific view, like an item in a list view or an image, to have a context menu associated with it. Then, when the system detects that long press event on that registered view, it calls a method in your code where you define and display the menu containing actions relevant only to that specific item, like delete, edit, or share. It's a great way to provide context-sensitive options without cluttering the main interface with buttons for every possible action on every item. Hashtag tag tag outro.
Wow. Okay. We have truly covered an incredible amount of ground today, from the underlying Linux kernel that really powers Android all the way up to the specific pixels and gestures and menus that bring an app to life on your screen. It's clearly a complex ecosystem, no doubt about it. But, understanding these fundamental building blocks, the stack, the components, the UI elements, it really does demystify how Android works. It feels much less like magic now.
Yeah, and if we connect this all back to the bigger picture, it really underscores the incredible modularity and flexibility that Google and the Open Handset Alliance built into Android right from the ground up. This layered architecture, this component-based design. That's precisely what has allowed Android to scale so successfully, to go from tiny phones way back when to huge TVs, cars, watches, and to adapt constantly to this endlessly evolving landscape of hardware and user needs. That thoughtful initial design is, I think, a huge reason why Android has remained so resilient and, well, ubiquitous.
So what does all this mean for you, listening right now? Whether you're just a curious user, maybe clicking around your phone with a bit more understanding now, or perhaps an aspiring developer feeling a bit more equipped.
Well, this raises an important question, maybe something to think about. Given Android's inherently open source nature and this highly structured modular component model we've discussed, how much more can we expect to see Android evolve? Will it continue to pop up in truly unexpected devices and forms? Is it going to further blur the lines between what we think of as a phone operating system, or maybe has it already reached its ultimate adaptable form?
Something to chew on next time you pick up your Android device. That's all the time we have for this deep dive. We truly hope you feel much more well-informed about the magic behind your mobile applications.
Yeah, thanks for joining us for this fascinating exploration into Android's internals.
See you next time for another deep dive.